This example comes out of section 7.1, Characteristics of Exponential Functions. Our basic exponential function is given to us in this form, y equals c to the x. So c is any constant here, so first of all let's title this thing exponential function. Different books use different letters for C, A, B, whatever. We're using C just to distinguish it from our A and B that we've used in transformations when we did stretches, because we will later on in 7.2 stretch these things. So let's take a look at y equals 2 to the x, maybe y equals 5 to the x, y equals 10 to the x, just to see what they would look like. If you have a graphic calculator, obviously you can just throw these in right away, but let's do the first one. If I had x and y equals 2 to the x as a table of values, if I put in a value of 0, let's say, 2 to the 0 equals 1. So if I'm graphing that, I'm going to have a point at 0, 1. If I put in 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. I can put in negative values. 2 to the negative 1, if you remember your exponent rules, is a half. 2 to the negative 2 is 1 over 4. And so what I'll have, if you draw some points and connect the dots, you end up with a curve looking something like this. And it does go through the point 0, 1. We could also label one of these other points, maybe 2, 4, since I'm not on graphic here, so you can see what we're looking at. So there's y equals 2 to the x. One thing we'll notice about it is no matter how big a number or small a number or negative or positive, this thing never gives me an answer of 0 or below, and this thing actually does have a horizontal asymptote at y equals 0. The larger the negative number you put in here, the further towards 0 this will go infinitely, but never actually touch 0. So there is no x-intercept. Y equals 5 to the x is very, very similar, and you can graph this one on your graphing calculator as well, and it will go through some of the same points, but it goes up a little faster. Because, for example, if I put in 2 for x, I can have 25 for y. So y equals 5 to the x is the same shape of curve, generally, same asymptote, same domain and range. The domain is all real numbers. The range has to be greater than 0. The asymptote is y equals 0. The y-intercept is 0, 1. But this one will go up steeper and down faster because the base is 5. 10 to the x would be even more so. It would go through the point 2, 100, so it's starting to head off my page. But y equals 10 to the x is, again, all of these are examples of exponential growth. So they're called growth because as you go to the right, each of these equations is getting larger and larger and larger, each value of it. And so y equals 2 to the x, y equals 5 to the x, y equals 10 to the x. So you could imagine that y equals 3 to the x would be somewhere in between two of the curves we've drawn here, 2 and 5. If we had y equals 100 to the x, it would be an extremely steep curve. We'd have to really play with our window settings to even see that one. So in the next example, we're actually asked to draw these curves if they have a base less than 1. So for example, y equals 1/2 to the power of x. Now if you started off with a table of values of this one as well, you would find the numbers are going to look familiar to you. 1/2 to the 0 equals 1, 1/2 to the 1 equals 1/2, 1/2 to the 2 equals 1 over 4, 1/2 to the negative 1 equals 2, to the negative 2 equals 4, to the negative 3 equals 8. And what you'll have is a graph that looks an awful lot like the first one we drew, except for it's not growing exponentially, it's actually decreasing exponentially. It still has an asymptote at y equals 0, has the same domain and range, still even goes through the same y-intercept of 0, 1. But if I'm labeling a point, for example, I have the point negative 2, 4. So the graph of y equals 1/2 to the x is essentially a reflection of the graph of y equals 2 to the x. We call this exponential decay. The reason why they call it decay is it often relates to radioactive materials decaying, but basically when you, in the exponential function back up here at the top, when you have c is greater than 1, you have growth. When you have c between 0 and 1, you have decay. We won't put in any negative numbers for C, because as you would see if you put in some values, you don't get a continuous graph at all. You just get a bunch of points all over the place. And we won't put in 1 for C, because 1 to the power of anything equals 1, and so you have a horizontal line, which is not particularly interesting and isn't really an exponential function. So exponential functions consist of growth and decay. We'll look into them some more.